Sorry, I'm a little bit late because the earthquake. Okay, yeah, because for me it's a little thing because I have experienced the really very uh, horrible earthquake in 2008. But for yeah, it's quite safe. Yeah, it's quite safe. No problem. When you are back to Chengdu, you will know that Chengdu is quite safe city. Okay, even in some this area, there's some place of Sichuan, I mean, there will be earthquake, but Chengdu is always safe. Okay, even for 2008, Chengdu is okay. So next time, if just when you are here, when you just feel that a little bit shaking of the building, so don't worry, just um, don't be scared. Just stay there and it will be okay. It will be fine. But because my mom and uh, daughter, I just need to talk with them. So sorry for the late. But anyhow, please be back to the meeting room and we will continue our study. And we have finished the learning of the mass center, mass moment inertia. It's very important to calculate the mass moment inertia because later on we solve the collapse of the rigid body will always involve rotation and general plane motion. We will need to write down the equation of motions for the rotating body, for the body doing general plane motion. We need to use the mass moment inertia. Okay, so how to calculate the mass moment inertia is very, very important. Actually, for most simple geometries, you just can refer to the textbook to find out the mass moment inertia. But you need to use the parallel axis theorem often, frequently to use the parallel axis theorem to find out the mass moment inertia about any axis. So to be careful here, the parallel axis theorem, okay. The mass moment of inertia of rod of mass m and L about to a transverse axis locate at its end. Oh, we have already calculated this. So which one about at its end? This is the rod, the mass is m, length is L. We need to calculate the mass moment inertia about its end. Which one? We already did the calculation, right? The answer should be C, okay? You can calculate by yourself. The mass moment inertia of a thin ring of mass m and radius r about the axis. Which one? This one is obvious. You take the differential element dm and the distance to the axis is r everywhere, right? So can you tell me the mass moment of inertia? Yeah, very good. Thank you very much. Yes, thank you. Okay. So mr squared. Okay. So the mass moment of inertia of any body about its center of mass is always maximum, minimum, zero, none of the above. Which one? The mass moment of inertia of any body about its center of mass is always B, minimum, because according to the parallel axis, right, it will equal to Ig plus md squared. So it will always be the minimum. Okay. If the mass of body A and B are equal, but Ka equal to 2kb, then the mass moment inertia Ia will equal to which one? We know this K means radius of duration, right? Just now I just give you the example. What does this mean? Radius of duration. Okay, so if the radius of duration is given, the mass moment inertia will equal to m k squared. So the answer should be which one? C, right? Yes. The radius of duration is given. Okay. So now let's figure out together because we don't have enough time. Okay. The density of the object is given. We need to find the radius of duration. Here, we need to find the radius duration. How to find the radius duration? If we can find IY, right? We can find IY and then IY define the mass. Take the square root, we can find the radius of duration, right? Because we know the radius duration is ky is actually, if it's given, equal to mky squared. Okay, so first we need to calculate the radius, calculate mass moment inertia about y-axis. And then you need to decide which differential element you need to choose. Here we use a disk element to calculate the mass moment inertia about the y-axis, and then we can find the radius of duration. The disk element of radius y and thickness dx. Thickness is dx, so because here is y, we take the just like here. Okay, so dm will equal to the density times the volume. Volume equal to pi y squared times dx. Why pi y squared? Pi y squared is actually, because here is radius of the disk is pi is y, so the area of the disk is pi y squared. Pi y squared, and then pi squared times the thickness will be the volume, right, of the disk element. And y is a function of x, so we replace the y with x, we will have uh, this. Okay, so this is the element, and then according to the definition, will times the y-axis, the x, the distance to y-axis will be x squared, right? So x squared dm, and then this one will be x cubic, okay, and then the lower limit will be 0 to 100. We can calculate it here, and then we can find out about the y-axis. Okay, and here, sorry, I think just here, the differential moment of inertia about the y-axis passes with the center of mass. Okay, passes with the center of mass, because here we use parallel axis law. Okay, so diy is given. Okay, because here for this for this disk, okay, for the disk element, and we need to calculate the differential moment of inertia, okay, about the y-axis passing through the center mass is given already. What does this mean? This here about its y-axis, sorry, about passing through the center of mass, okay, passing through the center of mass, and then it's given, you can check your textbook and you find out the mass moment inertia of the disk element, and it's given, and then using the parallel theorem, we have the diy equal to the mass moment inertia about its mass center plus dm plus the perpendicular distance between the two axes. And then we found out the differential, the mass moment inertia of the differential disk, and then integrate to determine the mass moment inertia of the whole object. Here, one thing I think maybe we need to figure out together is here. We take the disk element, right? And just like here, this is disk element. Okay, but it's the sequence dx. We need to calculate the mass moment inertia about the y-axis path with center of mass. At the previous slide, we have calculated the mass moment inertia about z-axis. Oh, sorry, the axis is actually perpendicular to the disk. Okay. Sorry. Here, according to the coordinate should be x. Okay, but here should be y-axis. Should be here, just like y-axis. You see, y-axis should be here. Okay, parallel. Okay, y-axis, and then for this axis, we can calculate the mass moment inertia. For this, you can take just like to calculate the y-axis, and then you can do the same just like before. Here, actually, we have this. You can do the calculation by yourself, but here we have this. You see here, this is the circular disk. For the circular disk, for the axis is 1/2 mr square, but for xxyy, here xxyy, so it will be 1/4 mr square. Okay, so calculate this. But one thing I want to ask you, just like for the disk, when you calculate the mass moment inertia about z-axis, we take the shell element just like this, right? But when you calculate the mass moment inertia about here, just like y-axis, how do you choose the element? You also need to choose the element, right? This y-axis. Can you tell me how do you choose the element? You can choose just like this one, right? They have the same distance to y-axis, and so this one, and you find out this dm and times the distance will be here will be r square, and calculate dm and then integrate. You will get the mass moment inertia about y-axis. Okay. Anyhow, you just can use this directly. Okay, in exam, this one will be given to you. Okay, this one will be provided. Okay, you only need to apply the parallel axis theorem. Okay. So mass moment inertia is really, really important. Okay, so we have done the problem together. It's a little bit complicated for the mathematics. Okay. So here, equations of translation motion for a rigid body which is doing translation. We know that we can regard it as a particle. Okay, so here exactly, but sometimes we know that, well, sorry, not just even for the translation, it will for every point on the translation body, they will have the same displacement, same velocity, same acceleration, right? Just like here, this is a boat, and the boat undergo rectilinear motion. Okay, we need to find out the reactions at the trainer wheels and the acceleration of the boat of its center mass. We can draw the FBD for the boat and the trainer. Okay, so we can write down equation of motions, but how many equations of motion do we need to solve this problem? So what are they? This is what we want to solve here. So again, we will limit our study of panel connects to rigid bodies, and they are that are symmetrical with respect to a fixed reference plane. Just as we have discussed in chapter 16, when a body is subject to general plane motion, it will undergo a combination of translation and rotation, just like first translate and then rotate, or first rotate and then translate. It's up to you. So for the problems, just for the problems of which body, the first thing is to establish a coordinate system. Here, the coordinate system is arranging and the arbitrary point P is given is here, just like here. For this rigid body is doing general promotion. Then we just establish the coordinate system. Okay, the XY axis again should not rotate and should be fixed or translate with constant velocity. So the acceleration of the coordinate system will be equal to zero. We call it an inertial coordinate system, right? So for a body, if the body undergoes translational motion, then the equation of motion is the sum of the external forces equal to m times ag. G is the mass center. This one we already know. This one we know that already because for the system of particles we have derived this, right? So this is a vector equation. We can also use its scalar form, like the resultant force of the external force system, the x component of the resultant force equal to m times the x component of the acceleration of the mass center. Or in y direction, we have the y component of the resultant force equal to mass times the uh, y component of the uh, acceleration of the mass center. Okay, so generally we will have the FBD. FBD will be the wheel force. The wheel force is acting to the rigid body. Just like here, the weight, well, we have the force F1, F2, F3, F4. We also have the moment acting to the rigid body. This is FBD. We also we have the KD. KD we know according to what we have learned, KD will be the inertial force and this inertial moment. Okay, MAGX, MAGY, MAG is inertial force. Okay, MAGY is one component of the inertial force. We also have the inertial moment. This one we will talk about later. Okay. The effect caused by the moments of the external force system, the moment about point P can be written as this one is the this one is for this one here. We take the moment about the P. We know according to what we have learned before, it will be the position vector of any force cos the force. Okay, this one will be the moment of the about point P. Okay, the sum of the moment of about point P, M1, M2. Okay, moment about point P will be equal to this, and so here from the for this one is equal to Rg cos MAG. We know this one because Fi equal to MAG, right? Fi equal to the according to the equation of motion, the force Fi will equal to mass times Ag, and this one will be Rg. Here, sorry, the derivation here is a little bit complicated. Okay, here it's just give its final forms. Let me tell you this way. I don't think I don't think it's good for you to understand. It's easy for you to understand here. Let's write down like this way. Okay. Here we have sigma F equal to mag. Before we have talk about this way, okay, we have the F, we have the mass, we have the velocity, we have the acceleration, right? We have the distance. This one, mass, is the resistance to the velocity change, right? Or is the resistance is a measure of the resistance the uh, to the translation. The force, actually, the effect of the force is to translate the object velocity, okay, acceleration for the translation and the displacement, and then we introduce the moment, right? The moment is actually is to measure the effect of the force to rotate the rigid body, right? This is a moment. And then we have the mass moment inertia. The mass moment inertia is the measure to the resistance to the rotation. For rotation, we have the angular velocity. And for rotation, we have the angular acceleration. We also have angular displacement, right? And accordingly, for this one, from this one, we will have F equal to ma, because according to the equation of motion, F equal to mass times the acceleration. Similarly, we should have the moment F corresponding to moment will equal to the mass moment inertia. M will be replaced by the mass moment inertia. A will be replaced by the angular acceleration. Okay, definitely here for the moment, we need to specify the point, which point you are calculating the moment, and which point you are which axis you are talking about the mass moment inertia. Okay, we have F equal to ma is for translation. M equal to I alpha is for the rotation. So similarly, we know that we have um, this one, mv, right? Mv is what? Mv is for the linear momentum, right? And then we will have angular momentum. Angular momentum, we know for a particular is like this way. And so for rigid body, angular momentum will be I omega. Okay, M corresponding to I, V corresponding to omega. Okay, so every question you just, I know it's easy for you to memorize the equations about translation. So when it is related to rotation, just replace the terms for translation to the terms of rotation, okay? So here, because the derivation process here is simplified, it just uh, give the final formula here. So I know most of you just will be confused. So I just would like you to just to understand the equation just by what I have told you, just like that way. Okay. Here, the term sigma mkp is called the kinetical moment about point B. Okay. It's a kinetical moment about point B. If point P coincides with the mass center G, this equation reduced to the scalar equation that's sigma mg equal to ig alpha. So here you say sigma mg is just like the mass moment. Sigma mg is it's not it's the moment of the real force system about the mass center. G is the mass center. Sigma mg is the moment of the force system I mean, including the F1, F2, F3, F4, and the moment of F1, F2, F3, F4 about G, and the moment about M1, M2. Because sure, definitely the moment of M1, M2 about point G will be the same, right? So sigma mg, you need to calculate, use the FBD to calculate the real moment. Okay, the moment, sorry, not the moment, the moment of the real force system. And Ig alpha is actually is just like here is the kinetic moment. Okay, Ig alpha is a kinetic moment about G, about the mass center, Ig alpha. So here we have sigma f G, sigma f, because f we don't specify G, sigma f equal to m Ag, right? The sum of the external forces will equal to the mass times the acceleration of the mass center. Similarly, we have sigma mg, okay, F replaced by m, moment. Sigma mg will be the moment of the real force system about the mass center, where equal to m should be replaced by the mass moment inertia. Ag should be replaced by the angular acceleration. Okay, so this one is actually just you just don't need to use this, just use this. Okay, it will be much easier. Okay, it will much be much easier for you to do this one. Okay, or why we have three questions? Because for sigma f equal to mag, this is a vector equation. So generally we can use its scalar equations in x direction, in y direction. So that's why here in total we have three equations. Okay. So every time you just you need to draw two diagrams, the real FBD and then the KD. Okay, KD is a kinetic diagram. Okay, KD will have inertial force, the kinetic moment, or we can call it inertial moment. You see here, MAG, MIG, AG, alpha. Okay, and then they just like equivalent force system. Okay, they just like equivalent force system. We know that for two equivalent force system, they should have the same equal resultant force, equal moment about any point. Okay, equal moment about any point. That's why here, sorry, we can just explain this way. It will be much easier. This is real force system again, FBD. Sorry. Again, we have FBD, the real force system. We have KD, right? We have FBD and KD. And this real forces, this is KD. KD will be inertial force, inertial moment. They are equivalent force system. For equivalent force system, they should have the equivalent resultant force, right? They also have the same moment about any point. This one is the moment about the mass center. This one is the moment about any point, right? So for the FBD, the moment about any point is sigma MP. And for this one, for the KD, you can calculate the moment about point P, right? The moment about P, how can you calculate the moment about the point P? How can you calculate the moment about point P? This one will be the same, right? But MAGY, it will be how to calculate sigma MKP, well, equal to X bar MAGX. This one is the moment of MAGY is a Y component of the inertial force about the moment of uh, this force component about point P, and this one, and then should be, because here this is counterclockwise, so it's counterclockwise positive, and this one clockwise right. We have the for the x component of the inertial force also have the moment about point P, okay, and then plus Ig alpha. Okay, so you need to calculate the moment about of the Kd, okay, of the inertial force system. You need to calculate the moment of the inertial force force system about any point P. Sometimes it's not easy for you to calculate this. So I will strongly recommend you to use this one. But sometimes we need this one, okay? So if there is only translation, definitely for translation, we know the acceleration of the mass center will be equal to the acceleration of any point on this rigid body, and the angular acceleration will be equal to 0. Okay, so we will have this one. Okay, sigma fx equation of motion equal to magx, sigma f1 equal to magy, and sigma mg equal to ig alpha, right? Alpha here is equal to 0, so it's equal to 0. You see, this is FBD, the wheel force system. This is KD. KD here, we only have the inertial force, the kinetic moment or the inertial moment here. Ig alpha is equal to 0. That's why when you take the moment about mass center, sigma mg equal to 0, because Ig alpha equal to 0, mag, the moment of mag about g is also equal to 0. But if you choose another point, just like P, here, another point, you need to be very careful. Here, we should have sigma mp is not equal to 0, right? Because Ig alpha equal to 0, but mag will have the moment upon P. So if this, the distance is R, so we will have R times mag. Okay, so be careful. You can regard them as force equivalent force system. Okay, so you can calculate the moment specifically. That's why here, note that if it makes the problem easier, the moment equation can be applied about other points instead of the mass center. This time, just like MA, choose A, okay, sigma MA, well, you could, sigma MA actually is the moment of the wheel force system about point A. So sigma MA again, sigma MA is the moment of the wheel force system about point A. Well, equal to MAG times D, okay? MAG is the inertial force, okay? D is actually the moment arm of the inertial force, okay? Very important here, okay? Sometimes, sure, definitely you can take the moment about the mass center, okay? So this one will be simplified to 0 because the inertial force will have no moment about the mass center. So when a rigid body is subject to curvilinear translation, this time, instead of XY coordinate system, we just prefer anti-coordinate system. Again, we can just apply the equation of motion. You see here, this is FBD, this is KD, and its mass center is G. This is an arbitrary point B. And again, we will have sigma F equal to MAG, the equation of motion, right? For translation, we have the sum of the forces, the resultant force of the wheel force system equal to the mass times the acceleration of the mass center. And then we use its N projection and T projection. And again, we have sigma mg equal to 0. What does this mean? Sigma mg equal to 0 is we just take the moment about the mass center. This one is the moment about the mass center of the wheel force system. You use FBD to calculate sigma mg. And then because we choose the moment about the mass center, the inertial force system will produce no moment, right? Because alpha equal to 0. We choose no moment about the mass center. However, if you choose arbitrary point B, and then you need to calculate again here, sigma MB will be the moment of the wheel force system about point B. You need to use FBD to calculate sigma and B. And then you need to calculate the moment of the inertial force system about point B. Here you have two components, the tangential component and the normal component. Okay, this is the normal component and the tangential component. And when you calculate the moment about point B, they will have the moment arm will be E and H respectively. It's very important here. Okay, so this is for the curvilinear translation. Okay, you can use anti-coordinate system, and you can choose the moment about the mass center or the moment about any point. Okay, and here one thing I forgot to point out is that the inertial force is equal to MAG, and the MAG and will have the same that so will have the same direction with the acceleration of the mass center. Okay, and you can take its tangential and the normal component. Okay, so that's why here MAG tangential. Okay, this is for translation. Okay, um, how to solve the problems. First, we need to establish the coordinate system, just like anti or xy inertial coordinate system. Okay, and we need to specify the sense of direction of acceleration, mass center, ag. It's very important. Okay, because we need to calculate them. The inertial force. Okay, and then draw a FBD, the wheel force system. Okay, and then draw KD. Okay, draw KD here, and for the FBD we need to show all external forces couples, and for KD we need to show the inertial force and couples. We mean the inertial moment. Okay, and then we identify the unknowns, and then we apply the state equations of motion. Okay, this is for XY coordinate system. This is for anti-coordinate system. Again, here, this one is for any arbitrary point. We calculate the moment about any arbitrary point. This is for FBD. Okay, this one is for KD. Okay, sometimes again we will have friction force. Okay, if we need to include friction forces, never forget that friction forces always act on the body, opposing the motion of the body. Okay, so reading quiz. When a rigid body undergoes translational motion due to external forces, the translational equation of motion can be expressed for the center of rotation, the center of mass, and the arbitrary point or of the bar. Which one? Undergoes translational motion due to external forces, translational equations of motion. Sigma F equal to MAG, right? Always the center of mass. The rotation about the mass center of the rigid body indicates that the sum of moments due to external nodes equals about the mass center of the rigid body indicates that sum of moments due to external nodes equal to the rotational equation of motion about the mass center of the rigid body indicates that sum of moments due to external nodes equals to Ig alpha. Okay. A 50 kg crate with rest on horizontal surface for which the kinetic friction coefficient is given, mu k is equal to 0.2, we need to calculate the acceleration of the crate if P is 600 Newton. Here, you see for the crate, it can translate only, right? But sometimes it can rotate, right? We need to find out the acceleration. So we need to know whether it's only translation and or there will be rotation or just general promotion, we say. We need to know this. Okay, maybe for this one we can figure out next time. Okay, we just tomorrow afternoon we will do this. Okay, that's all for today. Okay, that's all.